Welcome everybody to this so many edition of the Nobel Lectures in the University of Twente. Every time in the fall when the leaves are turning brown and yellow and red, and when the rain is coming, then there's a lot of excitement in science country because the Nobel Prizes are being awarded in the first week of October. But in the second week of October, there's a lot of excitement in the Netherlands community because then it's going to be decided who is going to give the lecture in Twente. And that's today. Where others are celebrating Halloween, we are celebrating the Nobel Prizes in physics, chemistry, and medicine and physiology. And today we have a fantastic set of three speakers who will explain everything about the Nobel Prize. By the way, my name is Gert-Jan Koster. I'm here a professor at the university, and I've been organizing together with Studium Generale and the faculty this Nobel Lectures. Also with my colleagues Kerenza Broersen and Hans Hilgekamp, as soon as the prize is awarded, we email each other who is going to be the lecturer for this particular topic. And it's always very exciting because you never know what the topic is, and then you also never know who's going to be the speaker. But anyway, without further ado, we're going to start with the prize in physics, a lecture given by Peter Kraus, who studied at ETH Zurich, who did his PhD in ETH Zurich, and then moved to Berkeley before coming to Amsterdam, where he now is working as a group leader at ARC-NL, which is a research institute of NWO, but is also assistant professor at the Vrije Universiteit Amsterdam. Peter is a known scientist in the field of attophysics, and has also won several awards for this, among ERC's starting grant. But I think we should start with the physics prize. Peter, the floor is yours.
Thanks a lot. And thanks, Gert-Jan, for the nice introduction. So it's my pleasure to report on the Nobel Prize in Physics tonight. And this was awarded to Pierre Agostini, Ferenc, Krausz, and Moungi G for experimental methods that generate attosecond pulses for the study of electron dynamics in matter. Now, that is a mouthful. So what does that mean? I'll start with the first sentence that the Nobel Committee themselves made. They said, this year's Nobel Prize in physics is about science at the timescales of attoseconds. That doesn't help too much either, I guess. So I'm going to try to break it down in this talk and answer the following questions. What is an attosecond? What do we need attoseconds for? What did the laureates do? And then finally, what can we do with this research in the future? Now here, I've written out for you what an attosecond actually is. So you have a 0, then after the comma, you have another 17 zeros, and then on the 18th digit there's a 1. So an attosecond is billions of a second. It's an extremely short time scale. So how can you imagine what that time scale is? Well, we have a pretty good feeling what a second is, right? Our heart beats once per second. So in the entire age of the universe, you have as many seconds or heartbeats. Well, there haven't been heartbeats for the entire time of the universe, but there have been seconds, as you have attoseconds in 1 second. And this is the ratio you have to think. Attoseconds to a second is like a second to the age of the universe. So it's extremely short. Now, what is actually happening on attoseconds? It's already kind of indicated here. What happens on these extremely long time scales in the macrocosmos, what you then have in the microcosmos are these extremely short time scales, and this is what's happening in attoseconds. Now, if you want to study something on these time scales, then you need to have a tool to record that. If you think, how do we actually observe things? How do we really observe anything? The answer is almost always with light. So what you need on the one hand is light pulses that are short enough, and you need to have a detection system for the light pulses that can record these fast events. So let's think about detection systems. Well, here I just have a video, and this is basically a video of a basketball that's hopping up and down. And in principle, What we're using now is our eye as a detection system of that basketball, right? And what you see are videos that are running at a different level of smoothness. And here you have 24 frames per second, and you clearly see there's some motion blur that's occurring. If you go to 30 or 60 frames per second, the video is running smoother and smoother. So basically at 24 frames per second, our eye can already not tell that these are individual images, but you realize that if you go to higher frame rates, that things are running smoother. So generally speaking, our eye has a time resolution of 50 milliseconds. So this is sort of the timescales that we can still perceive, very far away from attoseconds. Now, people realized quite early on that there are much faster processes than what can occur in 50 milliseconds. One example is the riding of a horse. And this video here was recorded in 1876. It's called The Horse in Motion, and it's often considered sort of the birth of movies, or the birth of, in that case, it was stop motion pictures. So Edward Muybridge set up a system to actually record how a horse is galloping, and from that he was able to tell or to settle a bet if during the gallop of a horse all the feet are actually in the air, or if the horse is always having a foot on the ground. And indeed the bet was settled. There is a time when all the feet are in the air. So this is basically to illustrate to you that already for a long time there were questions about what are shorter timescales than we can perceive with our human eye. And back then it was clear, okay, if we have a good illumination system and good detection system, we can record something that happens on the few millisecond timescale. Now you can already guess there are much faster things than horses in the world. And one of these things are electrons in atoms. Now, probably many of you have a science background, but maybe some of you not. So as a brief introduction, electrons are really the glue of matter. Electrons is what makes atoms bind together to form molecules, what makes molecules stick together to form more complex systems, proteins, what makes proteins stick together to ultimately form living cells. And all atoms are made of protons and neutrons in the core, and then the much lighter particles, the electrons that surround them, because they are so much lighter, they move on faster timescales. Now, how fast are these timescales that the electron move? And be mindful, all this motion of electrons is what's ultimately responsible for the reaction of molecules and then pretty much anything. Now, the timescales on which electrons move is indeed attoseconds. So this is one example from our research where we measured a charge creation and delocalization in a molecular chain, which in that case, it's evolving here. It looks slowly, but that's already sped up by a factor of 10 to the 18 approximately. So it's much faster in real life. What you see is that an electron hole, after it's created, an ionization, can transverse across a molecular chain in less than a femtosecond, 900 attoseconds in that case. This is still small molecules, so what is one possible application area? Well, something like ionization and then charge separation is what a lot of processes in nature start with. And one thing that has been studied a lot also here in the Netherlands is, for example, the initial charge separation in photosystem 2. So if you excite photosystem 2, there's an excitation and a charge separation and charge transfer occurring, which is unusually efficient. And this has often been speculated to be responsible for the relatively high efficiency of photosynthesis. So this coherent electron motion is often invoked as one of the reasons why photosynthesis is efficient. So with attosecond pulses, one dream is to follow such processes in real time. Now, how can we actually make such attosecond pulses? One of the most potent tools in the arsenal of scientists whenever it comes to controlled light production is the laser. I would challenge you to look for any year in the past years of Nobel Prizes where the laser didn't play some role or another. It's not always about lasers, but usually some chemist or physicist has a laser in their lab for some spectroscopy investigation. So the lasers are almost always, because it's a very directed and controlled way to make light pulses. And we often think of lasers like this laser that I'm using here as a continuous wave beam, but they're also pulsed lasers. And ever since the invention of the laser, people thought of ways to make faster and faster laser pulses. And that happened ever since 1960. That was when Mayman invented the first laser. pulses were made, first in nanoseconds, then picoseconds, and these pulse durations dropped down to the 5 femtosecond level. Now, if you would have told a laser scientist in 1960, in 20 years we can make 5 femtosecond laser pulses, probably that scientist would have said, this is going to be really difficult, but fundamentally it's possible. And the reason is, what you need to do to make these short pulses, create very broadband spectra, and at some point you need such broad bandwidth that you need to move these pulses more and more into the visible and ultraviolet range. Now the problem, if you go more to the ultraviolet, is this guy, or rather what he formulated in the early 20th century. And he basically said, if you want to make stimulated emission, the process that lasers are based on, this will become less and less favorable compared to spontaneous emission, and that takes over in the ultraviolet range. So it gets really difficult to make a laser at short wavelengths. There are ways to do that, but generally it's challenging. So this really seemed an ultimate limit. So something new needed to be found to overcome that limit. And that new process is what made these pulse durations drop to what is now 43 attoseconds, so almost 3 orders of magnitude again. And that process is called high harmonic generation. That's the underlying process to produce attosecond pulses. Now, what is high harmonic generation? High harmonic generation is the frequency up conversion of a fundamental laser. That means you shoot typically an infrared laser into a gas target, and what you get are multiple harmonics of the fundamental frequency. And that was one of the 2 first papers that reported high harmonic generation. And one of the co-authors is Annullier, and this was identified as the key publication that won Annullier the Nobel Prize. So it's this paper from 1988. Now, what is special about this high harmonic generation? Well, the first thing you could ask is, why is it actually special? Because some of you might have heard that there's something like a second harmonic generation. You can frequency double a laser. Usually this becomes extremely inefficient. And what was special is, if you look at the emission intensity, that's a linear scale here. You see that the 9th and the 11th and the 13th harmonic are all pretty much on the same emission strength. So it's unusually efficient. And at the same time, it's an extremely broad bandwidth emission that we're getting out here. And this is really the key to make ultra-fast laser pulses. So people pretty immediately used, not only is this a laser-like source in the extreme ultraviolet range, but we can make short pulses out of that. Annullier has really, ever since 1988, been one of the key players in that field, so she did many, many things after that, and was also always known for being extremely dedicated to her students. So it's also a nice anecdote. When she received the call, it was apparently very difficult for the Nobel Committee to reach her because she was teaching, and then she quickly went out in the break, and they only had a brief call, which she ended with a statement, "I find teaching very important," and she went back to her class and continued teaching. But then allegedly some of her students already figured it out that something was going on, and it was apparently very difficult to finish the lecture. Because of course, also the students knew she was a very famous person in the field of attosecond science. Okay, so this is what Annullier did. Now, how does that look like in the lab? Typically, you take a relatively short laser pulse of 30 femtosecond, shoot it onto a gas, and well, out comes the high harmonics. Make it sound simple. That's what a high harmonic spectrum look like. You have odd multiples of the fundamental frequency. And that's over an extremely large bandwidth, right? The visible range from 800 to 400 nanometer roughly goes then from 1.5 to 3 electron volts. So you have a 1.5 electron volt bandwidth. This is a 100 electron volt bandwidth that you can generate here. This is the key to make this a short pulse. That's one of the setups. We have to do that in the lab. So you have basically a gas expansion that comes here where you have this light matter interaction, and then afterwards some diagnostics, typically to look at the spectrum of the pulses. So now we zoom in here what's actually happening during high harmonic generation. So this is a gas jet where the gas comes out. And we have these little green dots here, and these are our atoms, typically noble gas atoms, and that's our ultra-fast laser pulse. That's a time-dependent electric field that oscillates as a function of time under a Gaussian envelope. Now the laser pulse propagates in time, and when the field gets stronger, what you see is that the outermost electrons start oscillating with the same frequency as the laser pulse. So they start getting polarized, and now they oscillate more because the field gets stronger. And once the field is strong enough that the outermost potential is sufficiently bent, then the electron can tunnel out. It's ionized, it's accelerated in the laser pulse, it picks up kinetic energy, it can turn around, and when it recollides, it can release all that energy in the form of an attosecond laser pulse. So that's the underlying model how this attosecond pulse generation works. It's this three-step model, that's what it's called because it's sort of 3 steps. It can be fully described with classical physics. It can also be done quantum mechanically, and then it's more accurate. But the classical model is what was done in these papers, and especially Paul Corkum has done a lot of the developments there. And Ferenc Krausz, one of the laureates, said, actually Corkum also should have received a Nobel Prize for that, but then of course it's limited to 3, right? Now, I've shown basically a continuous gas expansion, but if you do that with high repetition rates, you can do a better job if you pulse that. And a lot of the people in the field now actually use pulsed valve, and many of these are sold actually by Maurice Janssen, who has a company on that here in Twente, even though they're still called the Amsterdam valves because they were built in Amsterdam, so it's a bit of a discussion to be had. So both Pierre Agostini and Anhoulier got some by now, I think. Now, why are there high harmonics, or is it called high harmonic generation? Well, what I've shown you basically is one attosecond emission event in a half cycle of a laser pulse. So if you have a very short laser pulse to start with, then you get one major emission and maybe some satellite pulses. If it's a longer pulse, then you get a whole train of attosecond pulses. If you now look at the spectrum of these pulses, then this is effectively the interference of these pulses. And that gives us an either continuous spectrum for an isolated attosecond pulse, or this interference of one pulse every half cycle is what gives rise to the typical COM-like structure, and therefore the name high harmonic generation. So you get the high harmonics from the fact that you have an attosecond pulse train. And what's also interesting about that is that you get such an attosecond pulse structure even if you start with a relatively long pulse. Long here means 30 femtoseconds, or 40, that's also okay. And basically using, on the one hand, these pulses, and on the other hand, these is what Ferenc Krausz and Pierre Agostini were doing. Now, if you really want to make an isolated attosecond pulse, that's quite tricky because you need to isolate one of these singles half-cycle emission events. And the key is if you have a very short laser pulse, then one of the most intense emission events has a higher photon energy content. You can isolate that out either with a specifically tailored thin metal foil or a special multi-layer mirror. There was a lot of development in that, and that's what Ferenc Krausz did. So he was one of the first to manage to isolate first such a continuous spectrum and then demonstrate that this is an attosecond pulse. Oh yeah, that's what I said here. Now, once you've done all that, you need to measure it, right? This was all about how do we make the light, but how can we actually measure that? The trick here is you split the drive laser that generates these attosecond pulses, and you use one part for the high harmonic generation to make the attosecond pulses, and the other part you overlap in time and let them interact in a gas medium. So you shoot that together in a gas chamber and you overlap that here. So you need to do that with a time control of a few attoseconds. So if you translate that to a length scale, then 1 femtosecond will correspond on such a delay stage to 150 nanometer. So you need to have a precision of a fraction of that in such an interferometer. So this is what makes these experiments, besides all the laser infrastructure, extremely hard. And mind you, this is all done in vacuum. So I have turbo pumps and everything is shaking on the table, and still you need to maintain this stability. So that was then still took 13 years after the first high harmonics to demonstrate that there is an attosecond pulse. And then this almost happened at the same time. And Ferenc Krausz was the one who directly made an isolated attosecond pulse and demonstrated that this can be done. And that was the main paper from him that won him the Nobel Prize. And then a bit before Ferenc Krausz was actually Pierre Agostini, and he used a technique called RABBIT, that stands for reconstruction of attosecond beating by interference of 2 photon transitions, obviously. And And with that, he could also demonstrate that there was, in that case, an attosecond pulse train. Now, Ferenc, Krausz, and Pierre Agostini, I mean, career-wise, they are a bit different. Ferenc Krausz, besides being a brilliant scientist, really has then done many things. He has founded quite a few companies by now. I can think of at least 3, and maybe I'm missing some. And all of them are absolutely crucial to the ultra-fast world, because they basically made these tools accessible to many scientists to make attosecond pulses. And he's a director at the Max Planck Institute and runs an operation of, I think, 120 people. So besides science and business, he also has to do a lot of management, I presume. And Pierre Agostini, for most of his career, was a scientist at CEA Saclay. That's an institute in Paris. I think he ran a relatively small group with a few students and sort of always had creative ideas how to do these things. Particularly for the rabbit experiment, he also had some good collaboration going on. And that he right away mentioned in his speech or in the phone call that he had with the Nobel Committee. And he basically mentioned the co-authors on the paper. So you see how it often is in the paper, you have the sort of the last author who's sort of the leader of the lab or the collaboration, so that was Agostini. But then, interestingly, you have 2 authors that are from Amov, at that time it was called FOM Institute for Atomic and Molecular Physics, so that's basically our neighbor institute. And particularly Harm-Gerd Müller was really key as a former group leader at Amov to develop this technique, and he came actually up with the theory behind it and also invented the acronym RABBIT. Yeah, we actually had him over at AFCNL yesterday, so he still very much lives pretty much next to the institute, and he shared his experiences, so that was quite interesting. So what can we do with these attosecond pulses? I actually highlight the 3 examples here that were given by Ferenc, Krausz, and Annullier. And I think Pierre Agostini was too shocked when he got the prize. And he said, oh, probably I'll go hide a little now and have dinner with my family, and I don't have to give so many phone interviews. But Annullier first said she sees a big application in the semiconductor industry, and basically for nano-imaging of chips. One property that has not much to do with the attosecond pulse structure is that you make extremely short wavelengths. And they are short enough to diffract from the nanostructures that are now built in nowadays chips. So you can directly image the structures while they're being produced. And there is a certain company in the Netherlands that has a pretty big role in that, that I collaborate with a lot, and in fact Annullier as well. So that was always a bit of a link that we had there. And yeah, so that's actually the main application that she mentioned. Now, Ferenc Krausz mentioned 2 applications. The first one is also related to the information technology. And he said, well, with all these nanostructures that are now being done, basically we only gain computation speed by further shrinkage, by miniaturization. But we haven't really gained anything in clock rate for the last decade. So the actual speed of a processor hasn't increased. And what he demonstrated in 2013 is that with an ultra-fast laser pulse, you can switch a dielectric to become an insulator and back within a half cycle of a laser field. So that would, in principle, boost the clock rate from gigahertz, which is currently the standard, to petahertz, so 6 orders of magnitude. Now, this is done 5 times, because it's done with a 5 femtosecond pulse, and then at a repetition rate of 1 kilohertz, so it's still pretty far away from petahertz, but at least for 5 times it was shown it can be done on a petahertz scale. So that's further out, but it's interesting. And one thing Ferenc Krausz has recently been pushing is to use his attosecond technology to sample infrared waveforms and basically do ultra-sensitive and broadband infrared spectroscopy with attosecond technology. And that is being used for early cancer detection, so medical applications. That is probably even a bit further out, but they're even working on that in hospitals now, so it's also not completely out of the blue. Well, that I would like to conclude, and if you have any questions, please let me know.
Very interesting, very fast, and I'm sure there's some questions from the audience. So if you do, please raise your hand and I'll bring you the microphone. Any questions from you? Yes, there you go.
Thanks for the talk. You mentioned that you needed the starting laser pulse to generate these shorter pulses, but what is stopping us from using these short pulses to create even shorter pulses?
Yeah, that's a good point. So you need to have, to do that, you need to have a pulse that's intense enough to trigger ionization, right? And ionization typically, I mean, we're not living in an ionized environment. You need very short wavelengths typically to ionize air, but we're doing this with 800 nanometer here. And that's only working because it's such a high intensity that you can bend the Coulomb potential such that an electron tunnels out. So it's called tunnel ionization. And for that, you need extremely high intensities. Now, high harmonic generation is dreadfully inefficient. It has at best 10 to the minus 6 conversion efficiency. So what you're getting out is not intense enough to initiate another tunneling event.
Clear? Yeah. More questions? Yes.
So there was a part when you showed the molecule and like how the electron density went from the carbon to a certain element. And I'm actually curious what that compound is and if I can find anything about the research.
Yeah, you can read the paper, of course. This one. This compound is iodoacetylene. We had it specifically made for that experiment by chemists, so that you even get in the supplementary material, you will even get the synthesis of that compound. It was basically made because we knew from quantum chemical calculations beforehand that by ionization, it should be possible to create such a migration of a charge, and that's why we chose it. And the way you can imagine that is, well, you have this sort of this acetylene unit, and then this big polarizable iodine. So if you ionize, then it's likely that this polarizable big iodine loses an electron first, and that's sort of also what came out of the experiment.
Yes, thank you.
Are there more questions? Yes.
It seems pretty fast, the attoseconds, but is there some relation to the speed of light? Is there a minimum or?
So the speed of light is 3 times 10 to the 8 meters per second, right? So I gave a similar talk earlier, and then the question, so maybe that also your question then, was how fast would light actually travel in an attosecond? Yeah, so then you have 3 times 10 to the 18, and you want to go 10 to the 18 for a time of 10 to the minus 18 seconds, right? So then you're at 3 times 10 to the 10 to the minus 10 meters, so 3 angstroms. So in that time scale, an atom light can basically go about for separation of 2 atoms, 3 angstrom. So there's not yet a fundamental limit or so that we're hitting, but to give you an idea.
Okay, there's still, yeah.
Can you allude a little bit if the 43 attoseconds is sort of reaching the limit, or are you able to get them more phase coherent and even shorter? Or because there's a problem with the phases of the different harmonics. Well, not a problem, but
So the harmonics are by nature chirped. So actually the different harmonics all have slightly different emission times. So the pulse is not as short as it should be. And this metal filter that's used sometimes for filtering part also sort of gets the frequencies together. So in principle, that is not limited to make short pulses there, but the problem is a bit how can you accurately measure how short the pulse is. And there the 43 attoseconds is already quite at the limit of what can be reliably set. So you can make pulses that are below 100 attoseconds and that have a larger bandwidth than the 43 attosecond pulse, which then should be shorter, but it will be very difficult from at least these measurements to reliably say if they are so short. What you can think is if the pulse energies go higher and higher, and then you can measure regular cross correlations of the XUV pulse with itself. And that is also not a perfect technique for pulse characterization, But at some point it will be more accurate than these streaking type measurements, which have some approximations and get trickier the shorter the pulses are. But we're not hitting a fundamental limit yet, and the broadest spectra that were generated so far had almost 1 kilo electron volt bandwidth with high harmonic generation, and they would support sub-attosecond pulses, so septosecond pulses. Only from the bandwidth, but nothing measured.
Okay, maybe one final question. I think everything is clear then. Thank you very much. Let's thank Peter once more. Thank you, Peter, for a very nice lecture. And then it's time to move to the next Nobel Prize, or the lecturer of the next Nobel Prize, Daniël Vanmaekelbergh, who originally is from Belgium, did his PhD in Ghent, and then since a long time is in Utrecht, where he now is a group leader, a professor in the group, studying the topic of the Nobel Prize of Chemistry. Daniel is also a laureate of many prizes, among others the ESC Advanced Grant. And Daniel, I would like to give you the floor and explain us everything about the prize in chemistry.
Thank you, Gert-Jan. So, a few weeks ago, Moungi Bawendi, Brus and Alexei Ekimov got the Nobel Prize in Chemistry. I will start with presenting what the Nobel laureates have done. Then I will go in depth to the scientific impact, in depth relatively seen. And then we start with end with some applications. And then it's you for the questions. So, let's start with Alexei Ekimov in let's say the beginning of the 80s of last century, a long time ago. He was a researcher in St. Petersburg, and he worked on the properties of glasses. He studied inclusion of copper chloride. For God's sake, I don't know why copper chloride, but it was at the time probably a good guess. In glasses to change the color of absorption color of the glass. But what he found by XRD experiments, so by X-ray experiments, that by having this copper chloride in the glasses, small nanocrystals in the melt were formed. And what he found more is that by exciting them by, for instance, UV light, they were emitting quite monochromatic light. And when he heated the glass more, the nanocrystals were growing, and the emitted light shifted more to the red. So it became, the photon energy became lower in energy. And he got the good idea about what was happening. He thought these nanocrystals confine an exciton, an electron hole excitation, and due to this confinement, it's a very fundamental quantum mechanical phenomenon. We call it quantum confinement. Due to this quantum confinement, the electron hole pair gets, or the exciton gets extra kinetic energy, and you see this back in the emission of the light when the exciton radiatively decays. So this was experiment and directly the good interpretation. Some remarks. Well, first of all, we already had a semiconductor industry which from the gas phase made semiconductor heterostructures, and they had formed heterostructures where you had quantum wells, where you also see this confinement. But this confinement was only seen in one dimension and not in 3 dimensions at a time. And there were earlier reports of glasses which have in fact seen the same phenomena as Ekimov saw, but didn't make the connection to quantum mechanics. Second laureate, Brus. He tried to synthesize small crystallites in liquid media, water and alcohols. And one of the systems that he studied were nanocrystals made of cadmium sulfide. And he also found, when he excited these crystals, that they emitted light, and that the photon energy of the emitted light became higher when the nanocrystals became smaller. And he also, totally independently from, we were during the Cold War, and there was not so much connection between Russia and the United States, totally independently, he came with a model of quantum confinement, which you can all read about this in this, I became a bit too enthusiastic, sorry for that. You can all read this in these papers. So two people, totally independent from each other, not knowing each other at that time, they found out a very fundamental property in quantum mechanics, quantum confinement. Opsluiting in Dutch. So, some small remarks about this. This type of nanocrystals were also studied in the Hans Meyer Institute in Berlin, and they also have found very, very similar phenomena, but they were not so much interested in theory, and they, at least the group leader of that time, Professor Arnim Henglein, thought it has nothing to do with quantum confinement at this time. So that's a pity for him. Well, he passed away about a decade ago. He would not have been alive anyway, but he was a very nice guy, and he basically learned us the job of making small nanocrystals at that time. So we are in 1985. The principle of quantum confinement is recognized, but the nanocrystals were there was quite a lot of uncertainty about this. There was the synthesis was not good, and the number of nanocrystals or types of nanocrystals that show this emission, this typical emission related to the size, this number was very small. And synthesis and so on was very unreliable. And this has everything to do with defects. The way the nanocrystals was made was just a precipitation technique where ultra-fast crystals grew, but with a lot of defects. And you also had a surface, because if you have a crystal of a few nanometers, you have more surface atoms than bulk atoms. So that was a very, very big problem. And if that would be all, the field would have remained small, and it would have certainly be not a Nobel Prize for what has happened so far. But things changed. In 1993, the first-year professor, Moungi Bawendi, which came from Bell Labs, where he already worked on nanocrystals, started in MIT a new research group, together with PhD students, a few PhD students, among other Christopher Murray, and they start to think, how can we make these nanocrystals better? And they started from solid-state physics, and they thought we can grow big crystals of semiconductors almost without defects. They grow very slowly at high temperatures. So let's try to do this also in our nanocrystal synthesis. So what they did is finding out a slow synthesis by using other type of precursors, organometallic precursors, which decompose very slowly in the atoms that you need, and do the synthesis in organic solvents, highly boiling solvents. Second element. And third element, use these, now I have to see that I press on a good thing, use these capping ligands that do two things. They coordinate the dangling bonds on the surface, and by having almost the same chemistry as the solvents themselves, they keep the nanocrystals from coagulation. So there were three very fundamental principles in one synthesis. And it worked. It was a fantastic success. These are cadmium selenide nanocrystals, not the original ones of Christopher Murray, which you can find in his science papers, but nanocrystals that we grew much, much later on. And these are chemistral-night nanocrystals of 6 nanometer. These are chemistral-night nanocrystals of 3 nanometer. And this is all chemistral-night with decreasing diameter. And you see these one emit monochromatic light upon excitation with a UV lamp. And these, very similar chemistry, but just smaller, emit blue light because they are smaller. We all have to thank this, and I think Moungi Bawendi has already expressed his thanks to this very bright PhD student at the time, Christopher Murray, honorary doctorate at the University of Utrecht also, which played a really seminal role in this type of synthesis. He was the guy which thought that precursors which react slowly and only at high temperatures would be the real secret to get defect-free crystals. He not only made these defect-free crystals, but they were also very monodispersed. They are so monodispersed that if you dry out the solvent, they organize themselves as atoms. So what you see here are atoms of atoms. Each of these balls contain about 1,000 to 5,000 atoms, and they organize themselves, and you can, each of these little quantum dots, nanocrystals, can be considered as an artificial atom in a type of solid. That became later on his new type of research that he did at the University of Pennsylvania. Scientific impact. Scientific impact is very much about the physics of these confined compact excitons. First of all, what we directly see with our naked eyes from these nanocrystals are two very fundamental quantum mechanical principles. First of all, that particles with very low mass, light particles like electrons, have also to be considered as waves. Second, if we want to look to stable states in such small nanocrystals, these waves are standing waves, and standing waves for stable solutions means that the phase of this wave has to be constant all over the nanocrystal. And that is only possible when a natural number times, so natural number n can be 1, 2, 3, and so forth, half of the wavelength fits in the diameter of the nanocrystal. So we have standing electron and Hall waves. The Hall is a particle which is in fact due to the absence of one electron in the valence band. That's a little complication. Electron Hall waves or exciton waves in such a nanocrystal. If you assume that these are standing waves, that is this equation, and if you assume also the very fundamental principle of de Broglie, that electrons are waves, so that the wavelength is directly related to the momentum, and this is the constant of Planck, you can directly compute the extra kinetic energy of confining these electron and Hall excitations in the space of the nanocrystal. You immediately see that here you have a quantum number n, that's for the number of the state, and here you have 1 over d square, the diameter square of the diameter of the nanocrystal. Which means if the nanocrystal becomes smaller, the kinetic energy increases and the total energy of the exciton also increases. That's why when they decay radiatively, that small nanocrystals emit in the blue and maybe in a UV for very small nanocrystals, and that larger nanocrystals emit in the red, and they can go to the infrared as well if you make them still bigger, until they are so big that they have the same properties as the bulk crystal, so the bulk semiconductor crystal. That's the very fundamental physics principle, but that's about the exciton, but you can also furthermore unravel the exciton in their components. We have a standing electron and Hall wave, and with optical spectroscopy you always create an electron and a Hall, but there are other ways of spectroscopy, which we call electron tunneling spectroscopy, where you can use a metallic tip at a certain energy to inject purely an electron in such a nanocrystal. And this injection, tunneling injection, is possible if the energy of the electrons in the tip is resonant with one of these levels. That means that you can study electrons without the presence of holes and valence holes without the presence of electrons. Well, in optical spectroscopy, you always have electrons and holes. So what you have here is single particle spectroscopy, as we call, and the comparison with optical spectroscopy gives you a direct idea of the electron-hole interaction in these systems. Second unraveling is due to this person. This person is Sasha Efros, which also worked in St. Petersburg and helped already at the early times Ekimov with understanding what happened with the light. Later on, he became very famous for showing that, in fact, this exciton line is composed in a fine structure of several lines, which has to do with the locking of spin and momentum together. So you get an angular momentum, and you get, instead of one line, you like in molecules and atoms, the state becomes separated in a number of lines according to their angular momentum. And only the lines with angular momentum 1 can radiatively emit a photon, which also has an angular momentum of 1, to the ground state. Okay, that's what about science. This fantastic synthesis led to an enormous development, and hundreds of groups really worked on very different aspects, all related to nanocrystals. So there was the exploration of chemistry and surface chemistry to make core cell nanocrystals. Also, this strongly emitting nanocrystals was not limited to 6 materials, but also 3,5 group 4 materials, and now the perovskite family became very famous. And another thing that was important is that these nanocrystals could be kept and could be used as fluorescent labels for biochemical research. They were also used as single photon light sources in photonic crystals. That was, for instance, work that Willem Vos here at the University of Twente did together with us in Utrecht. Resulted in beautiful papers about the spontaneous emission of nanocrystals in a photonic environment where the density of states is quite limited. But of course, these bright nanocrystals also led to applications. There are many applications, but the most important one, which was displayed in NRC, is not something that will bring human life further. It was the invention of this very good type of television screens. So the bright quantum dots at different sizes were used as fluorescent emitters in these screens. They are also used in displays, and maybe, very probably, they will be used in lightning too, but these are harsh conditions and the stability of the nanocrystals is still a problem. But of course, maybe for later, things that are much more, let's say, concerned with our sustainable society are the use as biolabels in vivo and in vitro cell research, very important to detect cancer cells, and for instance, and maybe in the future also that these nanocrystals will be used as single photon sources for quantum technology applications. Thank you for your attention.
Are there any questions? Yeah, please.
So from my, is it on? Yeah, okay, so for my study I learned that quantum dots are really useful for biolabels because they're quite big actually compared to other labels, but they have a really low photobleaching effect. Yeah. Can you maybe explain how and why?
Yeah, so they still do photobleaching, but less than biomolecules, usually. And that's because, well, you see it here. You have the original core cadmium selenide crystal, And normally you have then already capping molecules, but you can also have inorganic layers which form electronic barriers. They passivate the original surface, but they form also an electronic barrier such that the electronic contact, quantum mechanical contact with the environment becomes less and less. So you have a bigger sphere, and inside you have the active material which forms where the exciton is confined. This helps enormously. This also helps in chemical stability. And if you want to make a bio system of that, you have to further cap it, for instance, in something biocompatible. That can be, for instance, a silica sphere or titanium dioxide. And then when you have this, you can connect this to a bioactive molecule or which finds its place or does something in a cell. But the stability is due to these inorganic cells, which were not in the original synthesis, which came later by many other research groups which were working in that field.
Thank you. More questions? Yeah, Peter.
Yeah, thanks a lot. You said something about the angular momentum selection rules, and I tried to figure that out, but I think I didn't manage. So I thought if we get an orbital angular momentum change, it needs to change by +-1, and multiplicity, spin multiplicity needs to be conserved. So then the total orbital angular momentum should be 0 or +-1. But you said it can only go from 1 to 1.
So you have, of course, the angular momentum plus the spin momentum, which forms the big Y momentum, and this, when you have a transition, this should change with 1 unit. But there are many combinations. You can have a spin 1, 2 combined with an angular momentum of, let's say, -1 or -2 or +2, and so you have a number of different states. You saw that this simple state was split in five states, among 2 were really optical active. Only 2, yeah. And the very nice thing is that you can have dark excitons. They, in fact, in principle, would have infinite lifetime. So they make very interesting things for quantum information processing, if you wish. Because you can, with the magnetic field, you can reverse them to bright excitons again, and then they emit.
For the experts. Thank you. Any more questions? I have a question myself. So you mentioned the first 2 Nobel laureates, or the ones you discussed, sort of independently discovered the effect of quantum confinement. But how independent is that? Because I mean, they also did it in sort of the same time frame, I guess.
They did it in the same time frame.
So how? What is? I mean, is it really independent?
Well, it's very clear that they didn't know from each other, but of course, and that is in my remarks, the principle of quantum confinement is, first of all, in all first year's textbooks in quantum mechanics. The particle in the box is something you all learn, and then you have to see that these nanocrystals are the boxes. But quantum wells were already, I looked up to the literature, and I found 2,000 papers on quantum wells already, where the confinement in one direction was already known. So you could argue that they got the prize for finding out that also self-standing nanocrystals, which are not connected to another semiconductor, can do the work.
So they sort of connected the dots in the right way.
If you wish, yeah.
No, but I mean, it cannot be completely independent. But it was the right time to do this kind of discovery, I guess.
Yeah. So that certainly. They certainly knew, and certainly also Efros, which worked in the Yoff Institute, which helped Ekimov. They knew quite a lot about the work of, for instance, Alfarov, another Nobel Prize winner in the Yoff Institute on hetero semiconductors, where in 2 dimensions the motion was free, but in 1 dimension it was already confined, and everybody knew it was quantum confinement. I remember when we started our group in around 1990, that the only thing we wanted to see was quantum confinement. That was the first principle. So this was not so mysterious, to be honest.
Okay, all right. Any more questions? There is still some time left, so if you have any burning questions. I see no hands, so then let's thank Daniel once more for the explanation, and then move to the final speaker of tonight, Gorben Peilman from the Wageningen University, and he's going to explain everything about mRNA. I think maybe all of us maybe have had mRNA in one way or another in the recent years. I mean, I don't know, but maybe some not. Gorben did his PhD also in Wageningen and then moved for a while to Australia and coming back in 2007 to continue his research in Wageningen. And you're going to explain us everything about mRNA, please.
Thanks very much. Yeah, so my name is Gorben Peilman. I'm from Wageningen. I've entitled my talk, Don't Shoot the Messenger. It's about messenger RNA, but I'm also your messenger today. So I will convey the message from the Nobel Prize laureates to you, and do not blame me at the end of it. It's not my work. The Nobel Prize for Physiology and Medicine went to two people, and here you can see a cartoon of them. These people are Katalin Karikó and Drew Weissman, and I will introduce these people during the talk while they made the discovery. And so they received the Nobel Prize for their discoveries concerning nucleoside base modifications that enabled the development of effective mRNA vaccines against COVID-19. So that's not all unclear, because mRNA vaccines against COVID-19, I think, are quite well known, and maybe you can raise your hand if you had an mRNA vaccine, just to get an idea. Yeah? Okay, maybe you got multiple shots. Who got some side effects as well after the vaccination? Yeah, some? Yeah, I did too. Yeah? Yeah? Was okay, yeah? Yeah, to curb the pandemic. All right, so that's not difficult then. Nucleoside base modifications may be a bit further away from what you're used to in your daily life. So I'll explain something about that. But first of all, I need to reiterate what messenger RNA actually is. So every living organism has a DNA genome, and eventually we want to convert the genes that are in the DNA. We will convert them into functional molecules, and these are the proteins. And that cannot be done in a single step. So what cells do is they make carbon copies of genes through this molecule called RNA. And if the RNA codes for a protein, we call it a messenger RNA. So a messenger RNA is a functional RNA that codes for a protein. RNA, in contrast to DNA, is very unstable. So RNA in a cell does not have a long life, will be degraded by your cells, will be degraded in your body. And that makes it also an interesting candidate, for example, for use in vaccines. Now, RNA, just like DNA, is made of nucleotides, and there's 4 letters. There's an A, C, G, and a U, whereas in DNA, the U is a T. Now, why are messenger RNAs interesting for vaccine development? And to understand that, we have to have a look a little bit at the history of vaccination. And in the old days, people did not know what they were doing, but they were using live viruses for vaccination. This is a very dangerous thing because you may kill people. So then later on, science progressed and attenuated viruses were made that were passaged in the laboratory, or you could inactivate them with chemical compounds or radiation. That makes them a lot safer. Then came the really exciting time of recombinant DNA technology, and we could basically make any protein that we wanted in every sort of expression system. And also here, the vector vaccines, for example, the Janssen vaccine, that technology was developed. But all these types of vaccines, they rely on biological systems. So they need cells, biological cells, to be grown in a laboratory or in a bioreactor. And that makes it also unpredictable, unreliable, costly. And if you could just make messenger RNA encoding for a protein, that would solve a lot of these issues because you can make RNA synthetically. in a chemical laboratory. It is fast, it's very reproducible. So for a long time, people have thought of RNA as being the ideal molecule for vaccination. But it has taken a long time before we were there. Now, Katalin Karikó has been instrumental in getting these messenger RNA vaccines to people. And she's an RNA scientist from Hungary from 1955, and she did her postdoc and PhD in Hungary. Then she had to leave Hungary at a certain point in time, and then she moved to the US. And there she started working at the University of Pennsylvania, and she's been there a very long time. Then at a certain point in time, she also joined BioNTech RNA Pharmaceuticals as senior vice president, and this is the company that eventually brought one of the mRNA vaccines of COVID-19 to the market. Currently, she's a professor in Hungary and also an adjunct professor in the United States, but I imagine that she is not doing much active research at the moment. She will probably give lectures worldwide for the years to come. So Katalin worked on messenger RNA and really wanted to work on that molecule to express proteins in cells. But that was problematic, because what is the problem with messenger RNA? So, as I told you, messenger RNA is produced in cells of all organisms, but between organisms, the messenger RNA differs a bit. And cells are very clever. They can discriminate between molecules that are self and non-self. And that is important because you want to keep bugs out. You want to keep bacteria out. You want to keep viruses out. So for a cell, it's a good thing to recognize self from non-self. And what Karikó ran into is that human cells react very strongly to bacterial RNA, and you get an inflammatory response in the cells, and these cells start secreting inflammatory cytokines like TNF-alpha, tumor necrosis factor alpha. And this is a chemokine that signals that something is wrong. And this happened a lot in her research. So, inflammatory response, good for the cell, but not good if you want to express a protein with a messenger RNA in a cell. And so, at a certain point in time, Karikó and Weissman started working together. And this is a picture from one of their papers, and I think it's a really important one. I'd like to guide you through it. So what we see on the y-axis is TNF-alpha secretion. So this is a measure for an inflammatory response. So the higher, the more inflamed the cell will be. And when they started transfecting different types of RNA in these cells, they could see what effect that had. And what you can see is that all the mammalian RNA, so for example human RNA that was purified and was then transfected into human cells, did not give this inflammatory response. And that is normal because it's self-RNA, is not recognized as foreign. When they started transfecting in E. coli RNA, so bacterial messenger RNA, you can see this massive upregulation of TNF-alpha, and that is a huge inflammatory response. So that's also good, as what you expect. But what they did here is they made RNA in vitro, and that is how the COVID vaccines now are also made. In vitro RNA, make it in a test tube in the laboratory, and then, again, this huge inflammatory response. And for many, many years, this has obstructed the development of messenger RNA for vaccination. So the research got stuck, and Katalin was at the University of Pennsylvania, and then at a certain day she met Drew Weissman at the copy machine. And they were had very different personalities. Karikó was a good sense of humor, very outgoing, chatty, talking about RNA all day long. And Drew Weissman was an immunologist, much more introvert, and really focused on his immunology and science. But still, they started chatting, and they told each other about their problems in their research, and they started joining forces. And really, from then on, it became a joint effort. And you do not see that always with Nobel Prizes. Sometimes there are competing people who do discoveries, but here it was really the two of them doing the work. So Drew Weissman is a physician and immunologist. It's really not a party goer. He has a medical degree and a PhD from Boston University, and then did clinical training at Harvard Medical School. And he did a postdoc at the National Institutes of Health. He had a research group in 1997, from then onwards at the University of Pennsylvania, and that's how he ran into Katalin. He's now a professor in vaccine research and director of the Pennsylvania Institute for RNA Innovations. Now, I've crossed paths with Drew once, twice. We never really spoke, but we were in the same event. And as a matter of fact, in 2018, the University of Utrecht had organized a symposium on novel vaccine platforms. And they invited Drew Weissman as the keynote speaker. And here you can read the title, mRNA Vaccines, a New Era in Vaccinology. And so he kicked off that day, and I had never heard of him actually. And he started talking about his research, and he presented his really nice ideas as how he converted the RNA and made it more efficient, and really showed that you can vaccinate animals very efficiently with these RNAs. And it's much better than all the other vaccines that were out there. And that talk kept on going with successes, kept going and going and going. And you were thinking, oh, this is a person bragging, a United States scientist just only showing the positive results and never talking about the negative. So we were very skeptical, and in the breaks we were also talking about it in that way. And in the next year we saw him again at a virology conference, and the same sort of talk. And I think the general skepticism was also there, and so we did not really believe in that messenger RNAs could really do this. And we felt it was cherry picking in the results. But of course, we were all wrong. And so this often happens in science, that some people do breakthroughs, but you do not recognize it at that point in time. You only see it 20 years later. Now, this is not 20 years. But anyway, so this turned really quickly. And Drew Weissman